Okay, welcome to the second vodcast on standing waves calculations, which actually is the final vodcast for all of the standard level waves topics, although many of these topics are revisited and expanded as part of topic 9, wave phenomena for higher level students. So it's the same basic instructions before, but we're going to actually have a look at solving problems. The example we're going to use doesn't actually look at all of these, but the content will cover this topic. And again, it's worthwhile looking at the guidance. Actually, I think we'll look through that at the end just to make sure that we've covered pretty much everything. So let's remind you of what we were looking at before. We have these three different modes of oscillations. And in each one, you can picture these. These are diagrams. So theoretically, they could refer to either a physical piece of string, like in a guitar or a violin, or it could refer to the air pressure across a boundary or something, although that would be unusual because this is a situation which has a boundary condition of a node at each end. And so the first thing we can do is relate the wavelength to the length. So in this middle one, the second harmonic, then we have one complete wavelength. I can trace it out either in that direction or in that direction, it doesn't matter. But it's one complete wavelength is equal to the length of the oscillator, the physical length of the oscillator. And so the wavelength there is equal to L. That's the second harmonic. The first harmonic, it's only half the wavelength. For the third harmonic, you have 2/3 of L. And so you can have this relationship 2L, L, 2 over 3L. Now, speed equals frequency times wavelength, as we've seen before in this unit. And therefore, frequency equals the speed divided by the wavelength, which we can apply that equation here. Frequency equals the speed divided by the wavelength. And it's actually frequency we're probably more commonly interested in most applications, because when we're talking about things like musical instruments, which is a major application here of standing waves, then we want to know what is the frequency that's produced by the length and the velocity. And we can actually take this equation and apply it to the real world. If you want to change the sound that you're making, the frequency, then a common way of doing that is by changing the length of the oscillator. If you're playing the violin, you put your finger down, okay? Or similarly with if you're playing the piano, then you'll have lots of different strings of different lengths. But you could also change the velocity. How do you change the velocity? You change the velocity by changing the material. So the different guitar strings all are naturally the same length or about the same length, but they are either made from different materials or from different thicknesses of the same material, both of which will affect the velocity. So going back to the equations, the frequency of the fundamental, the first harmonic, is V over 2L, V over L, 3V over 2L. And we can actually say that if this is a half V over L, we can split that apart and say that is the first, then V over L is twice that, and 3 over 2 V over L is 3 times that. So the frequency of the first harmonic is half the frequency of the second harmonic, and the frequency of the third harmonic is 3 times. So the frequency goes up by sort of one lot of frequency every time. 1F, 1F1, 1 2F, 2F1, 3F1. And we can generalize that, if you like, to say that the frequency of the 10th harmonic, so to speak, would be 10 over 2, which would be 5 V over L, so it would be 10 F1. It's a simple ratio. With wind instruments, it's more common to have a node at one end and an antinode at the other end. Again, we have this concept of L. A trombone is a good example, because a trombone you can change L simply by pushing and pulling on the slide. Similar mathematics applies, but with a subtle difference. So lambda 1 is now 4 times the length, because we've only got a quarter of a wavelength here. 4/3 L, 4/5 L. It's a different pattern. Since we have to have an open and a closed node, or a node and an antinode, sorry, we'll never be able to have a complete wavelength, because a complete integer number of wavelengths would involve having a node at both ends. We can apply the same equation, C equals F lambda, F equals V over lambda, and we can get the same principle here. So F1, and then this is 3/4 compared to 1/4, so that's 3F1. This is 5/4 compared to 1/4, so that's 5F1. So again, you have a first, second, third harmonic, but now instead of going up by a similar amount each time, it jumps. So 1F1, 3F1, so it's only odd values, odd multiples of the most fundamental first frequency. So first harmonic, third harmonic, fifth harmonic. You don't really get the second harmonic and the fourth harmonic on the same scale. And here's another example, but using panpipes, which are pipes which have antinodes at both ends. In this case, you can get a complete wavelength. Okay, it starts at an antinode and ends at an antinode, but it's still a complete wavelength. So that's a sort of third variety, which actually mathematically is pretty much the same as the strings with nodes at both ends. Okay, so that was a very brief look at the standing wave situation. In terms of guidance here, because be a little bit wary, the textbooks when they were written, particularly Hamper, and the dot point questions that you might be doing tend to be based a lot on the older standing waves, which I think went into more mathematical detail. I mean, you do still, this skill here implies you still need to know some of the mathematics, but perhaps not so much as you did. Students will be expected to consider formation of standing waves from only 2 waves. I mean, you can have 3 or 4 waves adding to a standing wave, but we don't need to worry about that. We have to consider different boundary conditions, such as 2 fixed boundaries, a fixed and a free boundary, and 2 free boundaries for both strings and for pipes. So it calls them closed and open, as I just did earlier, but fixed or free, it's the same idea. Standing waves and airs, we only not required the pressure. So one of the things I showed you did show a graph of pressure, but it's actually just the graph of displacement you need to worry about. And the lowest frequency is called the first harmonic, and we don't use terms like fundamental and overtone. So I may have heard those, and you may, if looking at past paper questions, come across, or old textbooks, come across the terms fundamental, which just means first harmonic, and overtones, which are the second and subsequent harmonics, but you don't have to, you won't encounter those in the exams. In the exams, all you will encounter is first harmonic, second harmonic, third harmonic, etc. Thank you very much.